So welcome to everybody online. We're going to start the workshop soon with an introduction from Christine Corban, the Deputy Director. And then we will follow directly starting with the workshop itself. So Christine, just Christina.
Thank you, Pietro. Good afternoon, everyone, those present here with us at the GRC in ISPRA and those who are joining us now progressively online. I would like to welcome you to the workshop on on-demand mapping for artificial intelligence and for analyzing satellite and drone images workshop. I'd like to welcome our two experts, Silvio Giancola and Anthony Chopa, who will be delivering this workshop over the 2 days, the two coming days. And also, just briefly to introduce our two experts, Silvio is a research scientist from King Abdullah University of Science and Technology in the Image and Video Understanding Lab, which is part of the Excellence Center or the Excellence for Generative AI Center. And Anthony Chopa is a researcher at the University of Liège, working on computer vision, video analysis, and AI. I'd like also to thank a lot Pietro Ceccato and the colleagues from the team of the Copernicus Emergency Management Service at the GRC, especially the team on on-demand mapping for organizing this workshop. I also thank all the participants really for your engagement and interest and commitment in advancing this field. For those who are not familiar with the GRC, I'd like to briefly introduce the Joint Research Center, which is the European Commission Knowledge and Science Service. We provide scientific evidence and independent advice to support the EU and EU policies in all the, let's say, the thematic areas. And in the GRC, our unit, the Disaster Risk Management Unit, plays a really central role in the EC in addressing challenges related to disasters and their impacts. So our mission in the Disaster Risk Management Unit is really to enhance the EU resilience and EU preparedness to face the current and future crises. And to do this, we develop different, let's say, solutions from integrated situational awareness systems to risk assessment tools, but also early warning systems and decision support tools. And we try to improve anticipation and monitoring of disasters being related to natural or man-made hazards and analyzing the impacts of those disasters, including also the impacts of climate extremes. And we try also to support disaster risk management policies in different areas, in particular focusing on the prevention and preparedness to disasters. And one of the key components of our work is the Copernicus Emergency Management Service, and which is actually coordinated and managed by the GRC. The Copernicus Emergency Management Service, for those also who are not very familiar with this service, it aims to provide reliable and timely information to support disaster risk management activities, but mostly also response, and across the EU, it operates across the EU, but also beyond the EU. And I think that really this workshop represents a major milestone and opportunity for us to advance the technological developments in the Copernicus Emergency Management Service to tap into the new technologies, being satellite imagery or also the technologies related to AI. And I'm particularly also excited about the upcoming release or launch of the Sentinel-1 satellite next week, which will really be also a major milestone that will also improve our reactivity and the monitoring capabilities in the context of the Copernicus, for instance, to better monitor flood impact and the flood extent. And I hope that the outcomes of this workshop will be useful to implement on the new satellite data that will be provided by the Sentinel-1. And also in terms of for those who have seen also the program, over the next 2 days, there will be theoretical sessions, but also practical sessions, hands-on experience sessions. And so I really invite all of you to engage in this workshop, collaborate, ask questions, and I'm sure that really the insights will be very useful really for advancing our work at the GRC and the context of the Copernicus. And I wish all of you a fruitful workshop, and I hope also that you will cover beyond technical aspects the very important issues of validation of the results and what you call interpretability of the explainability of the AI, especially that you know that now the EU Act on AI has been now adopted, and one of the key requirements is the transparency and the explainability of the AI models. So I'm sure that you will also tackle this topic in those 2 days. Thanks a lot for everyone, and I really wish you an insightful and fruitful workshop. Thank you.
Thank you. Thank you very much, Christina. That's good. Just for a logistical point of view, if you want to interact with us, everybody who's online, you can share and ask questions through the chat. So we will be here to answer your question. And also tomorrow during the exercise, we will have also some backup from the KAUST University. People can answer the questions about the exercises there. So without any dragging longer, I would like to ask Anthony and Silvio to introduce themselves and to start the workshop.
Absolutely.
Thank you.
Well, thank you again for having us today, and welcome everyone to our workshop, Computer Vision and Deep Learning for Earth Observations. So I'm Silvio Giancola with my colleague Anthony. We're going to spend 4 days today, 4 hours, sorry, today, and 4 hours tomorrow to talk about different advances in computer vision and deep learning. Some introduction about ourselves. So I'm a research scientist at KAUST. I've been working in the realm of AI and computer vision for the last 10 to 15 years. I have a background in a master from the University of Strasbourg, from Strasbourg in a university called INSA. I did my postdoc, PhD, Polytechnic of Milan, just next door, and I've been 8 years as a postdoc and a research scientist at King Abdullah University of Science and Technology in Saudi Arabia. My expertise falls within image and visual understanding, ranging from satellite images to video to 3D in general. And today I'm going to focus exclusively on what I call Earth observation, so the application of computer vision and deep learning in Earth observation.
Yeah, and I'm Anthony Chopas. I'm a postdoctoral fellow at the University of Liège in Belgium. So I've done also my master's and PhD degree there. I traveled a bit to Denmark, to Saudi Arabia with Silvio as well. And my expertise really falls into the video understanding part and really on the semantics. So that was the topic of my PhD, understanding semantics in images and videos. I've done a bit of work on sports data, and this has become my major focus at the moment, but I'm also doing in many different topics such as autonomous driving, video surveillance, and of course, satellite imagery as well. So just to give you a bit of an outline of what to expect today. So first, Silvio will dive a bit into the fundamentals of computer vision. So this is so that everyone is at the same page of what it is when we talk about images, when we talk about videos, and he's going to present a bit the general framework of computer vision, also applied to Earth observation. Then I will start after the small break on the fundamental of deep learning. So here we're really going to try to demystify what is artificial intelligence, machine learning, deep learning, and really go into what it is as a science, really. So our goal here is not to tell you AI is magical, AI can solve everything. We're really going to give you all that you need to understand what is AI and then to take decisions based on your new knowledge. Afterwards, so Silvio will talk a bit about the different building blocks of AI. So starting from networks to other tools that are more adapted to analyzing images, such as convolutions and transformers. We're going to look into typical architectures that are used in the field. And finally, we're going to show some examples on Earth observation data. So we're going to talk about the famous segment anything model released by Meta and its particularization to geosatellite images, so GeoSAM. And Silvio will present also some other works like FLOGA and different works on Earth observation. And so for tomorrow, the hands-on session, Christina, you were mentioning The evaluation part, we're going to have a talk about that rather tomorrow, because it's good when we're talking about the evaluation that we have these real examples on which to show this part. And so in the hands-on tomorrow, we have prepared some Jupyter notebooks so that everyone will be able to follow along and do some exercises together so that you get hands-on experience, basically. So just before we dive into the fundamental of computer vision, I wanted to show you a bit why, so the hype of AI for computer vision so far. So here I'm showing the Google Scholar ranking of different venues, so across all scientific fields. And so, of course, we have Nature, so the journal on top. And if you see right there, actually, so those are the conferences highlighted that are related to artificial intelligence. And the second one is nowadays CVPR, so computer vision and pattern recognition, which is number 2 in terms of impact. So it's really a field that is booming. So we see every year this conference gaining more and more participation and also impact. And so if we have a look here so this is the number of submitted papers over the years at that particular conference, the number of accepted papers in red. We can see that it's really like going exponentially at the moment, especially starting in 2016. And I wanted here to show you a bit why it is only now that it is booming and not before. So actually, the first big important parts was the availability of graphical processing units, so that we call GPUs here, that have been used for deep learning, and this was around 2009. And it's an important part of our research is that we need high computation power for computer vision, as you may know. And so using, especially for deep learning, this started in 2009. But the hardware only does not do everything. And so actually we need also data sets. And in 2009 was also the release of ImageNet. Silvio is going to talk about it just later, but which was one of the big milestones of available data sets for research purposes. And this has really started the boom of computer vision and AI. Now, we have also, in terms of methodology, a first important building block that was released around 2012, which is the convolutional neural networks, also called the CNN, that you may have heard about, and that we're going to dive into the different building blocks of this CNN in 2012, which really improved a lot the performance of artificial intelligence method for video analysis. And the last thing, which is really just before this very big boom, is the availability of software. So here are libraries for using deep learning. And so once these have been developed and also improved, well, it became available to a lot of researchers, not only those doing really just pure theoretical machine learning, but anyone who had an interest in using machine learning in their own field and deep learning. And so here are two common examples, so TensorFlow and now PyTorch, which is the most popular among our community. So like I said, the important tools are hardware. So we need graphical processing units, which are usually stored in big servers, so with 8 or 16 graphical processing units per server. So this is an important part. If you want to do computer vision, you will need these hardware. We have the software part. So most of the research is done in Python with the PyTorch library that is well integrated within the NVIDIA CUDA language, so which is a language that allows to speak to the graphical processing unit and do all the computation in parallel, basically. And finally, we have the availability of data. So data is one of the most important parts of any computer vision or machine learning project. And nowadays there are tons of useful data sets that Silvio will present. So I will now leave the floor to Silvio for the fundamentals of computer vision.
If you have any questions, by the way, feel free to interrupt us. I mean, I prefer to have that as a discussion rather than a unidirectional discussion. Feel free to interrupt us also online if you'd like to have some questions. We'll be very happy to answer them. So let's focus now on the fundamentals of computer visions and the concept of understanding images, which is actually the building block of computer vision. So ideally, I have access to some data, so like for instance, these images of cats and dogs, and I would like to have a model, something that can tell me whether new data actually is a cat or a dog. Replace that from satellite images of house or building versus cars or something like this. We can actually want to learn something in the middle that would understand these images and provide you some information about that output. Sometimes you're actually interested in something more fine-grained. So you don't want just to classify images, but you also want to understand the images at the fine-grained levels. For instance, in this task of semantic segmentations, you want to understand that every single pixel of that image belongs to a specific semantic categories. For instance, a car, for instance, a road, for instance, a line, for instance, a building or sky, and so on and so forth. This is very widely used also in satellite images when you want to understand the different lens usage, for instance, of satellite images. Sometimes you also are interested in understanding more the instances that appears in the images. For instance, here you're not only interested of this is a pixel containing a car, you want to distinguish a car versus another car, for instance. So in satellite images, typically in terms of houses, you don't want only to understand that those are houses. You also would like to split them into this is the house number 1 or the house number 2, and so on and so forth. This task goes under the name of instance segmentations and sometimes object detections, which are basically boxes that bounce the images that are dot lines around those different objects. And of course, the application of those tasks are quite broad. You can apply that on images, on videos, that come from drones, that come from sports, that comes from any different field where you actually have data. Those algorithms are usually extremely, in deep learning at least, versatile. If you have the data to train those algorithms, you can actually apply those algorithms into your field. But basically, how can we understand images? Basically, what looks very easy for us, for instance, understanding that the 3 images on the left actually represent the number 3, it's a very trivial problem for us. But for a computer, it's a bit more complicated because the image of this number 3 is nothing else than a matrix of numbers that goes range from 0 to 1 that provides the intensity of that visual data. And the same goes actually with satellite images. But we have built a knowledge that allows us to understand that this number here is actually the number 3. And basically, deep learning is trying to do the same things with this data, trying to understand that specific inputs represent specific outputs. But let's dig first on what is actually an image. Most probably this is might be redundant for some of you, but it's also good to actually set down like the basics of what an image. An image is nothing else than a 2D functions that is parameterized by spatial coordinates x and y, also often called I and j, because they are usually discretized by the number of pixels. And the image, which is a function of the x and y spatial coordinates, provide basically an intensity or a color at that specific location. Grayscale images are basically scales of intensity of pixels, while color images are usually resulting to the component of multiple channels that combine together to represent a colored image. So those are basically matrix, or also called tensors of intensity of colors that range from 0 to 255 if we are in an 8-bit scenario. Some sensors, especially in satellite images, might collect like up to 10 bits or sometimes 16 bits that allow for some intensity that range above 255. And the key aspect is basically that an image, like you can see here on the bottom, is basically nothing else than a list of pixels that have different intensities, sometimes multiple channels, like the RGB channels for colored images. But what the computer actually really sees is nothing else than a matrix. And that's why it is challenging for a computer to understand that matrix without analyzing in details the structure of that matrix. So grayscale images are matrices, color images are tensors. Typically, our visual systems have some, like the human systems are basically sensitive to wavelengths ranging from 400 nanometers to 800 nanometers. That corresponds to a scale ranging from the red to the blue channels, wavelengths, and there is like a filter of barriers that exists that corresponds to 3 channels correspond to a wavelength of the red, or wavelength of the green, and wavelength of the blue that corresponds to more or less what we actually see as human. So color images are nothing other than tensors in a 3-dimensional space, so a 3D matrix. Of course, we can go beyond the visible spectrum, and this is one of the key advantage, one of the key components actually of usually satellite images is that they go beyond the visible spectrum. We don't only care about the visible spectrum that runs from 400 nanometers to 800 nanometers, but sometimes we are interested in the near infrared, the infrared, or some specific wavelengths. So we have the concept of multispectral and hyperspectral images that goes beyond just the red, the green, and the blue channels. How are those images stored? Usually, there's 2 types of representation, 2 types of vocabulary used in the literature. The concept of hyperspectral images versus multispectral images. Multispectral images is basically very similar to RGB images, but it contains usually more than 3 channels. Can take an arbitrary number of images that can correspond to different type of colors, sometimes beyond the visible field. While the hyperspectral images more often corresponds to really a curve of intensity in function of the wavelengths for a given pixel in the screen. But let's dig into what we are looking for from this data. So we have understood that images are tensors or matrices of data that corresponds to visible or beyond the visible spectrum of some wavelength intensity. But once we actually have those images, we would like to extract some information about that. We often talk computer vision is the science of understanding visual data. And here I would highlight 4 of those different tasks that are commonly used in computer vision. There is more, but I think those one are the most that covers maybe 80 or 90% of the use cases, which is image classifications, the task of taking an image and classifying whether it's a cat or a dog. Object detection, which is the task of placing bounding boxes around object of interest, like in the second image where we have 2 cats, 1 dog, and a duck. Instance segmentations, which is one level of granularity more fine-grained with respect to object detection, where we actually have polygons detailing the contour of that object. This is very useful if we are interested, for instance, in estimating the coverage, the pixel coverage of a specific object or a specific instance in that image. For instance, if you want to have the area of fire burned in some regions, you might prefer to have like an instance segmentation that defines the polygon in very fine-grained regions to estimate the area of this, rather than bounding boxes that might contain some background. And the 4th task that I'm going to highlight also today is the semantic segmentations, which cares a bit less about the instance that actually presents, but it's mostly a classifier for every single pixel. So we try to understand that there are a region that corresponds to cats. We don't identify whether it's a 1 cat or a dog or cat, a dog and a duck. That could be useful for a generic application. Of course, you can extrapolate that examples to satellite images where the cat and the dog and the duck might represent a specific type of vegetations, of agriculture fields, seas, or different areas. So in computer vision, we often talk about tasks. And the aim is basically to solve a task by building a model. Usually, when you actually want to solve for a specific task in computer vision, the first questions that you want to arise is, what is the output I actually want to achieve? Do I want to classify an image? Do I want to find a region of interest? Do I want to create a bounding box around a specific object? And most often that goes with, how do I evaluate the performances? Because eventually, when we're talking about different algorithms, we want the best algorithms, and we want to find a way to evaluate how that output corresponds to what I'm expecting, which is often called the ground truth. And usually the same question that people ask us is, which data do we actually have available? And based on the data that I have available, I would build a model that I can develop and sometimes train on this input data to provide a specific output that I would evaluate its performances form of scores, for instance. So some of the challenges that arise in the literature of computer visions, this is in the very general cases. One of the first data sets that was released to the community was this MNIST data set, which is image classifications of handwritten digits, the one that I showed you in the very first examples, where the scope is to classify 10,000 images among 10 classes representing the digits from 0 to 9. And usually those are grayscale intensity with very low resolution pixels, and it's one of the first data sets that was used in the literature to train neural networks, for instance, to perform specific tasks. Of course, this task is now almost solved. You have examples of algorithms that solve that at around 99.99% of accuracy. So this is almost a solved problem. Second data set of challenges that arise was to actually introduce some colorful color images, and in particular with the data set CIFAR10. CIFAR10 is an image classification of different types of objects. It has 3 RGB channels ranging from 0 to 55, a bit more pixels, 10 classes, 60,000 images. And what actually made the revolution was in 2009, as Anthony has introduced, ImageNet, which was one of the largest scale image classification datasets of colorful images, many different resolutions, a lot of different classes, and millions of images that has been collected by Professor Fei-Fei Li from Stanford, who recently actually got some pretty good awards about that specific work in particular, which is understood as one of the key elements that enable deep learning in the area of deep learning for computer vision. You might ask yourself, what is available in Earth observations, whether it is from satellite images or from drones, for instance. One of the first data sets that I could find in the literature was the UC Merced land use, which is an image classification task that corresponds to 21 different classes of objects ranging from harbor, intersection, golf course, forest, airplane, of images of 2056 by 2056 pixels, colorful images, and a total of 100 images per class. And that is the one of the first application of the image classification task in the Earth observation field. Then if we go a step further to object detections, which is the task of my input is an image and I try to have an output, which is basically bounding boxes. Pascal VOC in 2007 was also one of the first data sets that actually enabled some research in that field. That has almost 10,000 images, and a lot of objects are annotated in this data set. In the field of Earth observations, that would correspond to the DOTA object detection dataset. Again, from an image, I'm looking for bounding boxes of objects that you can slightly see here. You have a roundabout, for instance. You have some buildings that are spotted here. You have a lot of cars that have been detected here. Sorry if the images are very small, but basically those are large-scale data sets corresponding to almost 3,000 images and almost 200,000 instances of 15 common object categories that were in those very large-scale images of 16 million pixels. Going further to one level of difficulty, when we talk about instance segmentation, so the task of extracting polygons out of images, identifying different type of object. Another Pascal VOC challenge from 2012 was targeting object segmentations with a large number of images, segmentation, and different type of objects. In the realm of Earth observations, that would correspond to the dataset ISAID, which is also for instance segmentations. It takes the same images from DOTA, from the 2,806 high-resolution images, and in that specific case, it contains almost more than 650,000 object instances from 15 different categories. Some of them are actually shown here, like plane, helicopter, swimming pool, small vehicles, and so on and so forth. And again, the input are images, and I would like my model, my artificial intelligence models, or any computer vision algorithms to produce polygons that would identify where my objects are and how big those objects are in number of pixels. Finally, in semantic segmentations, one of the last tasks that I mentioned, where I'm mostly interested into classifying pixels, whether they belong to specific categories. Big EarthNet was one of the efforts for large-scale Sentinel benchmark archive. that is a land cover classification task, images that range from 1200 meters to 1200 meters with different resolutions. We have 12 channels because we're talking about Sentinel data, 19 different classes and a lot of images to tackle that part. Another one's called Deep Globe, land cover classification. Again, so a semantic segmentation task. The input are images and the output are actually asks for that. And from those different images, the scope is to identify the pixels of urban, agriculture, rangelands, forest, water, barren, or unknown, for instance. So that basically gives you an overview of like the different tasks, different how we define the concept of task from an input to an output with a model in the center that try to provide the output from that input. There's a lot of data sets that exist, and the data set was one of the pillars that made deep learning and computer vision actually that robust and that mature these days. So that gives like an overview of like the computer vision aspect. If you have any questions, I'll be very happy to take any. If not, we can proceed with the part of the deep learning.
I don't see any questions on the line, but if you have any questions.
I have one.
Of course.
So these datasets are defined based on some criteria, or which type of images and why are selected, and do they also evolve over time if more images are used and other models are trained?
Right. So usually the scope of a dataset is really to try to understand a task. So the scope of ImageNet being released, or Deep Globe, for instance, being released, is to try some generic algorithms to benchmark which algorithm is better than the other. Usually they are not meant to evolve in time, they are meant to be somehow frozen. They are built by researchers and released publicly to allow the research community to progress in that specific field. So usually the dataset itself does not necessarily solve the end goal problem of the users, but it provides a test bed to compare and analyze algorithms and basically benchmark which one is the best. Provide a fair comparison between the different methodologies. Usually it's frozen, but in a real case scenario, you can actually adapt that and you can actually feed more and more data in time. And the rule of thumb is the more data you have, the more performant will be your algorithm that you have trained on this data.
And if I may complement, so when those data sets evolve, they usually get a different name as well. So there will be a V1, a V2, and so on, especially to really separate what was done before. And if you want to test your new method and compare it to previous method, you need to have the exact same data set that was used to train and to evaluate. So this is the most important.
It's basically to compare apple to apple. So sometimes algorithms can be better than another, not because the architecture of the neural network would actually be more efficient. It's only because maybe you feed more data. Data is a bit more informative than another. So really to distinguish, disentangle the effect of the data and the architecture of itself, you usually take those data sets and freeze them. And still nowadays, people are using the same ImageNet that has been built in 2009, just to try to build a better architecture that basically provide a better classifier in general. Of course, that model as is not something that is necessarily useful for final use case. ImageNet, I think they have thousands of classes. I think half of them are different breed of dogs. Unless you're interested in the breed of dogs, there is no necessarily needs into actually learning how to classify those dogs. But it provides, a playground for researchers to build a classifier that will be able to disentangle some really fine-grained classes, like Dalmatians versus a different breed of dogs. So in the future, if you'd like, in the satellite images realm, if you'd like to classify a house versus like a tall building, for instance, maybe the visual traits are very similar to each other. Like especially from a top view, it will maybe look like a square. But if you have algorithms that are able to distinguish these very fine-grained differences, you would eventually be able to train some algorithms that will distinguish different types of buildings, for instance.
So there's like a score that every time it has to be better than the previous one.
Exactly. I like to think as like a two-dimensional map. So at a given time, I actually have one data set, let's say ImageNet, and I have multiple architectures that I would actually different like algorithms I would test. And the scope is basically to get the best performances. Once it starts saturating, maybe there is a new data set that actually arrives that is basically maybe more challenging. In fact, the ImageNet, there is two versions of it. There is a one called ImageNet 1K and 121K. The number of classes that are actually being used. The first one was only 1,000 classes, and at some point we're starting saturating. So they released a new data set that is more challenging with 21,000 different classes of objects. So of course, all the algorithms that were trained before will perform with a metric that is a bit worse than what they had before. So it provides a new test bed to improve again these algorithms.
And how is the benchmark done? Like these images, there's a version for training and another version which is pre-classified.
Right. Exactly. That's exactly what we're going to talk about. I mean, usually there is basically a challenge or test set that is used only for the scope of benchmarking how good is my output versus the ground truth, to provide you with a score of how good your algorithm is. But usually I don't. The best practice for deep learning is to not use this data to train your algorithm on, because there is a lot of problem of overfitting from whomever is actually familiar with that. I hope that answers your question.
Definitely. Thanks.
I have a question from the audience, from Lucas. He said, is there some place where the information on the large training data sets are collected and can be searched for? Or are these data sets proprietary and not available to the public?
Usually they are open source, so there is how to search for them. There is a really good one called Open Image Dataset. I think people can actually look at my image dataset from Google, which is here, the V7, where you can have here, for instance, this is the latest dates, the largest, I think, data set that exists right now. There is the second versions from the Google. It contains 15 million boxes from 600 classes. A lot of instance segmentations. Now people are also looking into relationship annotations, narratives, and I think you can explore them by just clicking on the Explore, looking for a random class. And is that working? Trying to select first orientation 1. Random class, and I would basically, I don't know what that is, but there's a class, for instance, Cessna 206, which is a type of airplane that basically has some annotations about the mask or the bounding boxes or the label of the whole image. There's a lot of data sets like this. Some research can actually help you figuring out those things.
Can I just a question? I know also there are lots of challenges in satellite imagery that, like for instance, the cloud detection and the cloud shadow. Does any of those data sets include also this, let's say, the specific challenge of, for instance, haze and cloud classification, which is still, I think, a very, let's say, it's a challenge for the remote sensing community. Right. And another thing about those available data sets online, if any of it contains specific data for hyperspectral imagery, because now they're much limited to RGB, but some multispectral, so for Sentinel-2. What about hyperspectral or radar imagery? Are there any specific data?
Exactly. Tomorrow we're actually going to use a data set called FLOGA. This FLOGA has been released a year and a half ago. It's about wildfire in Greece. They are taken from Sentinel-2, the Sentinel-2 and MODIS satellites images that are annotated with cloud coverage, with different land usage, and the geographic positions, the region, the polygon and the mask of where the fire was. And it was interesting because that data set, the reason why I picked it for tomorrow is because they have the same image of the same region from before the fires and after the fires. because there exists some specific algorithms that do not take only one image as an input and just expect one output. It can take multiple images and try to see the differences of those images to get the information of that region. So FLOGA would be one of them, FLOGA, and it's the one we're going to use tomorrow. I think there's a lot of them. And FLOGA also has actually multispectral images. Look, the spectrum of Sentinel-2, so I think it's 11 or 12 different channels from Sentinel-2. But there is, I think, at least dozens, not like 20 or 50 actually different data sets that have been curated. It's really important to have a curated data, because the more curated your data is, the better the training and the learning of the algorithm will be. There's different regime in training a neural network and an artificial intelligence from this data. If your data are noisy, which means that they are not necessarily well or weakly annotated, the performances of your algorithms won't be as good as if it was really, really clean data.
Sure.
I hope that answers your questions.
Yes, thanks.
Was that answering the question also online that we had?
Yeah, I don't see an answer, but I think, yeah, Lucas, if you are satisfied with
Okay.
the answer.
Happy to follow up also. Okay, so much. Okay, so without further ado, next step is basically towards deep learning, and I will leave the floor to Anthony for that part.
All right, thank you very much. So here we're really going to dive into the science of deep learning and really take a step towards the basis of what is artificial intelligence, machine learning, and deep learning. This is actually the first thing that I'm going to try to make, is the difference between these three vocabularies that we have. So artificial intelligence started in the 1950s, around that, and it's everything that covers rule-based methods, but it's very broad. Then we got the machine learning part that started booming in the 1980s, and that was used, for instance, for detecting spam emails in email address once the internet was available. And then the last part, which is a subfield of machine learning, is deep learning, and is the topic of today. So, like I said, first for the artificial intelligence is everything that is rule-based. So actually here I'm doing what we call segmentation of different objects on a grayscale image, and I'm doing it just by thresholding the value. So everything that is above a certain value, so let's say here 127, so between the range of 0 and 255 for the pixel values, this is a first very basic artificial intelligence model that just says I segment everything that is above that value. So yeah, this was a bit in the beginning of the 50s as well. Then we move on to machine learning, and here the objective is that I will provide some handcrafted features. So basically I will provide my model with some low dimensionality data. So for instance here it could be two classes that you see in red and green on the left. And I want to learn a decision boundary between these two classes. And so this falls, for instance, into the decision tree and random forest that I can learn. So it's not like I am making the rules. I'm just providing my model, so my decision tree, for instance, with a bunch of data, and then it will automatically learn those rules. So for instance, that it needs first to separate everything that is above or below x2 to say that some patient is, for instance, healthy here, and then say, okay, if it was not above, then I need to look at x1 and so on. And so this decision tree is learned, and this is machine learning. So basically going from low dimensionality data and learning just a boundary classification. Now the next step is what we call representation learning, which was a first step towards deep learning, which is instead of having to provide those handcrafted features, so for instance, in my previous example, it could be two different parameters from a blood test, I'm going to provide just the raw data to the model, and it will not only have to find the decision boundary, but also to learn what features would be interesting for that for that boundary. So I'm not going to tell the model that it needs to use the two particular samples from my blood test, but I will provide the whole blood test report, and then you need to figure out how to assemble the different ones and to provide. And the final step is deep learning, which here the model has become more and more massive, and we're able to capture really fine-grained data and to learn those features and those decision boundary in a very complex and deep architecture. So here is a common pipeline that Silvio explained before for computer vision, and of course for deep learning we have a very similar pipeline. And the only thing that we are going to add here is actually on the data part. So on the data part, there is going to be a difference whether you just have input data, so for instance satellite images, or if you have labels associated with that. Because we will need those labels not only to evaluate the model, but also to train the deep learning model. So for instance, this means that people have to spend time beforehand annotating bounding boxes on satellite images to draw masks and so on. I think we lost the sharing. Okay, are we back on? Perfect. Thank you very much. Perfect. So yeah, do I have labels? And so if I fall within that category, I'm in what we call the learning paradigm of supervised learning. So I have data and I have labels associated with my data, and the labels correspond to exactly what I want as output of my task. Now there are other learning paradigms that we will cover also today, which is first semi-supervised learning, where I have data and labels, but just for a subset of that data. And so I don't want to annotate, for instance, millions of images, but I'm going to annotate maybe 1,000 of them, but I'm still going to try to leverage all the data that was not annotated to improve my model. Then we have weakly supervised learning, where I have data and labels that don't correspond to exactly the output that I'm trying to achieve. So for instance, instead of segmenting and assigning to each pixel the value of the class that I want in the end, I'm just going to tell them, I have 3 cats and 2 dogs in this image, but I'm not telling you where they are. And then the model has to figure out. And finally, we have the self-supervised learning, which is very interesting to learn representation of interesting feature representation of the data that I want to analyze. And so this is also an important part because the data sets are getting bigger and bigger in size. So it's always, it's easier now to collect data, but it's still as costly to annotate it. And so here, this part is also very interesting because it allows to learn from unlabeled data. And so today, like I said, first we're going to focus on this supervised learning. And in this next section, I'm only going to talk about this supervised learning. So I have data and I have labels associated with it. So let's dive a bit into now the mathematical formulation of what we are talking about when we say deep learning model. So what we have is first this model that is parameterized by some parameters. And I'm going to introduce a bit of notation here, mathematical notation, but this is because it's the standard first in deep learning, those notation, and also it really helps to understand what is going on behind the scene. So the model is parameterized by some theta parameters. So it's a set of parameters. And here I'm writing theta 0 because we have to initialize the model at some point. So we initialize it usually randomly. Now I'm going to feed some input to the model, which are usually called X. So this can be images, multispectral, or RGB, for instance. And once I put in my data into my model, what I get is a prediction. This prediction can be anything, a segmentation mask, a bounding box, a class, whatever. And so it is dependent on both the input, of course, and also on the model parameters. Now, since we are in the supervised learning case, what I have associated to each data is also some label that I call Y without the small hat. So notice the difference between the two. And so my objective then would be for Y and Y hat, so my labels and my prediction, to be as close as possible, right? So we want the model to be able to provide the correct label depending on the input. And so how are we going to compare that? So I'm introducing a new notion here, which is called a loss function, which is basically some kind of distance function between my label and my predictions. So once we have said that, the objective of deep learning and supervised learning will be to find the optimal set of parameters of my model, so theta, that minimize this distance for my whole data set. So I'm going to just decompose a bit the equation here. So we can see that here we have a sum over, so here x and y, which belong to my data set. So this means that over my whole data set, I want to do something. I'm going to compute the distance, so the loss function between my predictions and my labels. So I want this distance then to be minimum. So this is why I have this minimum function here for while I'm changing my theta parameters. And so the objective will be to find the optimal set of parameters theta that minimize this loss function over my whole data set. So this is really like the objective of any deep learning model. Then, of course, there is different choices here. So what am I going to use as data set? What am I going to use as model and as parameters of my model? And what am I going to use as a loss function? So just to give you a bit of information about this distance function. So there are some properties that it should do. So first, it should reflect the objective. So if I'm doing semantic segmentation, I need a loss function that will be minimum when the segmentation mask is the same as the predictions, right? It should also be lower bounding. See, since I have a minimization to do, if my loss goes to -infinity, I cannot find the minimum, right? So it has to be lower bounded. It must be differentiable for reasons that I'm going to explain right after, and preferably convex, because optimization of convex function is always easier than optimization of any type of function. So I'm giving you two examples here. So for instance, in classification, one loss function that is commonly used is called the binary cross entropy. So here the label y can only have two values, either 0 for, let's say, background, and 1 for whatever class I'm interested in. And my prediction can range between 0 and 1. And so if we have a look just at the function here, so let's say that I'm in the case of y is equal to 1, so that my label is of class 1. So I'm going to just have this part of the function that is going to be used, and it's going to depend on the logarithm of my prediction. And so here you can see the function. So it's going to be minimum and at 0 if what I predict is class 1, and it's going to be infinite if I predict a 0 while it was class 1. So it's doing exactly what I want. When the prediction is different, so 0 compared to 1, the loss is high, and when I have 1 and 0, the loss 1 and 1, the loss is low and actually 0 because it's perfect. This is what we expect it to do. Now for regression problems, you may have already used this mean squared error loss function, which is basically just the difference between the value and the prediction raised to the power of 2. So these are two common loss functions. Now I want to take just an example of a simple regression problem, just so that we understand all the different parts. So here I have some input data values, so that are 2, 3, 4, 5, 1, and 0. And this can represent anything. So let's say it is any kind of index, NDVI, or the temperature, or whatever that is across different pixels. And I'm going to try to map something. So for instance, here could be the vegetation density or whatever. And I want to have a model that would link those input values right there towards the value that I want it to achieve. So here going, let's say, from an index towards a density, vegetation density value. And so then the objective will be to use that model to predict it on new data that I don't have the value for, right? So this is always the goal. And so here we're going to talk about a training set, because this is what we're going to use to actually train our model. So those first 3 values. So let me take a very simplistic model, the most simple that I can do, which is this linear model right here on the right. So here the prediction is directly linked to the input by a theta parameter. So y hat, my prediction, is equal to theta times x. So this is just a regular linear function. And I'm going to start with some initialization, like I said. So I can, for instance, start with theta 0 is equal to 1. Okay. Then I can compute all of my predictions based on my inputs. And so, of course, theta is equal to 1, so y hat is equal to x. And so, for instance, value 1, 2, my prediction is going to be 2, which is far from 8, of course. 3 is going to be 3, and 4 going to be 4. Now, what I want to do is compare the two. And so for that, I'm going to use a loss function, and I'm using the mean squared error, for instance. So you have the formula right here. I'm just doing this line here of labels y minus this line of prediction here, and raising to the square and summing over my whole training set. So 8 minus 2 squared plus and so on. And this gives me a number 261, which is basically the distance between my prediction and my labels. Now, what I want to do is to actually reduce that loss function to 0 if possible, but to reduce it as much as possible and find somehow the theta parameters that are going to be minimized. So one way we could think about would be, well, okay, let's try different theta values. So here I'm providing what we call the loss surface. So this is the loss value as a function of the theta parameter. So sorry, it's a bit small, but the x-axis is just the theta parameter, and the y-axis is the loss value. So before I was around here, theta equal 1, and 216 for the loss value. Now, obviously, the minimum is 4 for the example that I showed, and with 4, we actually have a loss of 0. So this is possible because we only have one parameter. Now, if we move on to more complex models, not just a linear model, we're going to have, for 2 parameters, something that looks maybe like this, so in 2 dimensions. And if we go towards higher dimensions, well, actually, the loss function can look something like this. And so if we want to do a brute force search, it's actually possible for very small models, but absolutely impossible for very large ones, because you have to take all the combinations of all the parameters, and this grows exponentially with the number of parameters. So it quickly becomes intractable to actually do that in practice. And with deep learning models, we're talking about hundreds of thousands of parameters, millions of parameters, or even billions of parameters for the largest models. So of course, this is not a good way to optimize the loss function. And now one interesting thing also is that usually the loss function is highly non-convex. So as you can see on the right, this is taken from the ImageNet dataset, if I recall correctly. It is a slice into the loss surface. And so as you can see, finding a minimum in this very noisy loss surface is actually difficult. And so there is a lot of research on how to optimize. But what we're going to see is one basic algorithm that is still used nowadays, and that is actually one of the standards in most projects to optimize our model parameters. So actually, what do we have access to? So this loss surface, like I told you, it's impossible to have it in higher dimension. So we can consider that this gray line, we actually don't have access to it. But what I did before was compute the loss value for one initialization parameter. So theta equal 1, and I had 216 right there. So this I have. And another thing that I can have is actually the partial derivative of my loss function with respect to each of the parameters. So this is why I told you that the loss function had to be differentiable, if you remember a few slides ago. And also the model needs to be differentiable. And in deep learning, this is the case. So all the building blocks that we're going to see later with Silvio are actually differentiable. And so with this partial derivative, this gives me basically the direction towards which the function is actually decreasing. So if I take a look here, you can imagine yourself at the top of one of the mountains that we can see from the window, and imagine there is a lot of fog around you. So you can only see like exactly where you are. And what you have to do is, if you want to get down the mountain, is look at your feet and basically see where the slope is decreasing and take a step in that direction. And this is exactly the idea with this first method that we call gradient descent. And so here in the equation, what you can see is that this is my parameter of my model at some point. So for instance, at initialization. And what I'm going to do is to change that model parameter with respect to its partial derivative of the loss function with respect to that particular parameter. And as you can see, I'm going in the opposite direction of the gradient. Why? Because let's take here the example. I'm at this point, the gradient is negative, so the function is decreasing. And so what I want to do is to take a step towards that decreasing, so going positive in the positive step. So here is what you can see. Also, another thing is that I'm going to take a step that is proportional to the gradient. And why do I want to do that? Simply because imagine that I'm here around the minimum. The gradient is actually very, very low. So I know that I am almost close to the minimum. So I have to take a smaller step than if I'm very far away, like right there where the gradient is very large, where I need to take a big step to reach the minimum. So this is like the idea behind. And what I need to do also is to scale that step with respect to one important parameters that is represented here by the eta Greek letter, which is called the learning rate. And we're going to see the role of the learning rate right after. Let me take back my example. So here what I can do is do the derivative of my loss function with respect to my parameter theta. And as you can see here, so this is the expression, sorry. This is the expression of the derivative of the loss with respect to that theta parameter. And so what I need to do is simply, so -2 times my label minus my prediction times the input. So I will let you derive the equation. It's actually very simple from the mean squared error loss function to actually derive this formula. And so if I do this, I see that I have to take a step of magnitude 174. So this means that, like, if we go back just one before, so that I have to update my theta parameter for the next step to do minus, so let's take 1 for the learning rate at now, minus 174. So this means that my new parameter is going to be 175. So I'm going in the right direction, right, compared to here. So instead of having 1, I'm going in the right direction, but I'm taking too big of a step. And so this is the role actually of the learning rate right here to reduce this step size. And so how do we choose the learning rate? There is no universal rule. I cannot tell you choose a learning rate of that scale and it will work for all of your project. It's like actually more like a cooking recipe. So you have to try out and to analyze a bit the training of your model to know if you have to reduce or to increase the learning rate. There are some guidelines on how to start, and people have tested on different data set learning rates that work. But basically, if you have new data set, new models, usually you have to tune that parameter. So if I take a parameter that is too small first, what is going to happen? Well, I don't know if you can see it very well, but here on the left, I'm showing the trajectory of the theta parameters as I train my model using this gradient descent. And as I'm getting closer to the minimum, my gradient is getting smaller, and my learning rate is staying the same, so it is at some value. And actually, every step I'm going to take a smaller step. And what can happen is that I can converge to something that is not the minimum, but just that I'm taking smaller and smaller steps and converging to some other point than the minimum. Now, if I'm taking, on the other hand, a too large value, what's going to happen is, like I showed you before, I'm going to go to 1 to 175, and maybe 175 to minus 216, and I can so on. And so this will actually make the model diverge. So this is called a divergent case. But if I choose it just right, I can maybe reach the minimum. Now, there are some strategies to update that learning rate during training. So usually at the beginning of the training, you use a very large learning rate to find the region of the loss surface where to look for, and then you reduce the learning rate to try to converge towards a local minimum and hopefully a global minimum if possible.
Sorry, how do you distinguish the local minimum from the global minimum?
You have no idea. It's impossible to know if you're even at a minimum first. So that you can you can look around a bit the space to see so where you end up if you are at a minimum, but you cannot know if it's the global minimum. The only way to get the global minimum is to do the brute force approach and explore all the parameter space, which is impossible. Yes.
Can I add something? This is the reason why we're actually hoping that every of the functions in the loss are actually convex. Because in the case of a convex functions, which is the convex function,
right, so you have only
the
one.
global, the local minimum is the global minimum.
Yeah.
But it's not something you have actually in very, very large
Data set
and neural network.
Yeah.
There is like some methods that somehow convexify a bit the loss function. So there's a large literature in convex optimizations, and they have some people working in non-convex optimization that try to convexify that functions to make it more smooth and a bit more towards like the global minimum. And there's also some good initialization parameters. There's one called the Javier initialization that was, I think, released maybe 5 or 10 years ago, which is somehow a good initialization for all your weights for convolutional neural networks or some other layers. That's in general actually converge very well to the global minimum. That's basically the rule of it.
Okay, I see.
Yeah. So now, if you recall a bit what I said before, is that every time I take a step, I had to look through all of my data sets, which was doable when I had only 3 data, right? So I compute the loss and the derivative of the loss for each of these data points. I aggregate them with an addition, for instance, in this case, and then I take one step based on whatever the derivative of the loss told me to go for each of the parameters. So this is doable with very small data sets, if I have 10 or maybe 100 of data points. But when I'm talking about millions of data points, it means that I have to predict with my model 1,000,000 times the value of the loss and of the derivative of the loss before taking a single step of optimization. This is highly non-efficient. And so usually what people do is that instead of doing just gradient descent, it's to do what we call stochastic gradient descent, which is actually very simple. It's just instead of taking my 1,000,000 of images, I'm going to split this 1,000,000 of images into small batches of data, so maybe 10 by 10. And then I'm going to feed them to the algorithm one by one. So this means that I'm just going to look at a subset of my data set that belongs to my batch, so my 10 data, and I'm going to take a step based only on those 10 data and then move on to another set of 10 data and so on. And so this is called the stochastic gradient descent, and it is actually, this is the optimization algorithm that is used in most of the research nowadays. So now just talking about a bit the methodology. So when I have a data set, like I said, you can split it into batches, but actually what we do is to split it into 3 big sets. So the first one is the training set that you see here on the left. And so the training set will be, like we've done here in the example, to tune the model parameters. So all the theta of the model, whether it is just my linear model here or any deep learning model. So this set is usually the biggest part of your, represents a big part of your data set. So for instance 2/3 or 3/4 of the data set, and it is really like what is going to be used to train the parameters. Then we have the validation set, which will be used to tune the model hyperparameters. What do I mean by hyperparameters? But, well, for instance, the learning rate that I have before. So I'm going to try out different learning rates, train each of them of the models with different learning rates on the training set, and then compare the values of the different learning rates on the validation set. And then I can select the learning rate that led to the lowest loss or the best performance based on this validation set. We usually don't do it on the test set because the test set, in theory, should be used only once to evaluate the final model that I have. And this is to guarantee that whatever you're going to develop, so tuning the model parameters and the hyperparameters, is going to work well on new data. If you start tuning either the hyperparameters or the model parameters on the test set, you're going to do what is called overfitting. And so actually when you're going to test it, so you're going to have great performances and you can put it in your paper and yeah, I got state of the art, but then if you test it on other data outside this test set, so in a real application, it's actually not going to work or going to work much less better. So yeah, this is like something we have to be very careful about. And so with Silvio, for instance, we organize challenges on different computer vision tasks. And what we do is we provide the test set to the participants, but we have no control if they're going to tune their model on this test set. So what we have is actually a fourth set that is called a challenge set, on which only us have the annotations, so they cannot tune either the model or the hyperparameters, the model parameters or the hyperparameters on this challenge set, and they can only submit predictions, and we give them once a score every month, for instance. So this is to avoid overfitting. And so, yeah, if everything goes well, what happens as I update my model? So here on the x-axis, you can see it's called epochs. So it means one run over my whole data set. So using stochastic gradient descent, for instance. Well, actually, the loss function or the distance between my prediction and my labels is actually going to decrease. So this is hopefully what we want to get, of course. But if we take a look at the validation set, what is going to happen? Well, at first, the model is going to also reduce the distance, but at some point, it may increase once again the distance between my prediction and my labels. And so what happens here is that the model is getting too good at doing the task on the training samples. And it's actually starting to find shortcuts or to remember some specific data points in its decision boundary. And this is something we want to avoid, of course, because we don't want to have the best model on the training set. The training set, we already have the labels. What we want to do is to leverage that model on any new data. And so this validation loss not only helps us to select the learning rates, but also, for instance, to know when to stop training a model. So here we can see that we should stop training the model around this point right here. And this is probably what's going to get the best performance on the test set and then on real data. Now one thing that I want to talk about is sometimes the data set size is a bit too small. So it's sometimes very costly to get images. So for instance, I'm thinking about in the medical case, if you want to have a big image of, let's say, the lungs of someone, well, you need to have to do some kind of scanner or MRI or whatever, and to have a doctor that looks into this data and that annotates everything. Or if you need to have, let's say, on some part of the world, you have a flooding, and the flooding hopefully doesn't happen too much in that part of the world, and you maybe have a few data points only to train on, right? And so one way that people have started to increase artificially this data set size is to use data augmentation. So as you can see here, I only have one data point of a frog, for instance, right there. And what I can do is actually to artificially create new data based on that. So for instance, I can flip the image, I can zoom in and crop a bit the frog, I can play a bit on the contrast or the tint of the image, And this is gonna lead to 5 different images here with the same class, so frog in this case. And this helps increase the size of the data set. And like Silvio said in the beginning, the size of the data set is usually one important part of the performance of the network. So for most of the challenges that we have right now, the more data, the better the model. And this is one way to do it at a very low cost. It's also, this part also helps with overfitting, actually. Because instead of feeding at every epoch the same image of a frog, and maybe, I don't know, the network finds a shortcut that this pixel right here that is in the eyes of the frog only appears black in this particular image. Well, if I only feed in that, maybe it will learn that rule that is absolutely dumb, right? And so using this data augmentation also prevents somehow to fall into these shortcuts for learning the network and provides better generalization usually. Now, another thing that you have in satellite imagery is, of course, class imbalance. So if you're looking at road versus everything else in the segmentation task, well, you're going to have maybe 1 pixel out of 100 that is actually a road, right? And the rest is going to be fields, is going to be whatever other type of classes. If we train a network on this binary segmentation task, what is going to happen is that the network might be a bit lazy somehow and find the local minimum where it only predicts background instead of road. Why? Because if he makes a mistake, well, it's just 1% of the data. So it will get 99% of accuracy, and it will think that it did a great job at its optimization, but actually this is not what we want. We still want the network to actually predict the road, right? So when we are in this class imbalance problem, we usually have this problem with the convergence of the training of the model. So there are a few possibilities that we can use. So for instance, the first one is to weight the samples differently in the loss function. So this means that if I know that I have a 20:1 ratio, for instance, well, if he makes a mistake, if the network makes a mistake on the road pixel, I'm going to penalize it 20 times more than if he makes a mistake on the background. And this will actually help to rebalance as if like the road was as important as the background. And so this is like a first way that is commonly used. Another one is to resample the data set. So this means to, if we are in a classification task, for instance, let's say that I have 20 images of cats, 1 image of a dog in my data set. I'm going to take this image of a dog and I can do data augmentation to create 19 other images of that same dog. And so then the network will be fed with tons of the same amount of images of cats and dogs during training. Now, this works also, but you have to pay attention to the diversity also of the data. So the data of the cat is going to be very diverse, while the one of the dog will be less diverse because it's the same image, so the same kind of information. So it doesn't weigh that much as well. Yeah. Or the other thing is just to sample every like 5 times the same image of the dog while we are getting the 5 different images of cats as well. So yeah, this was a bit all the basics of how to train artificial intelligence models. So like here, what you have seen is very generic, right? I didn't talk about a specific architecture, whatever. And so now we will have Silvio, who will present the different building blocks. And I just want to finish with one thing, is that now everything seems to be solved, right? We know that we could put any kind of model, we can do the optimization, and hopefully we will get to the minimum. But actually, it's not as easy as that. The first, training is complex. So like we said, we can have issues with convergence. We can converge to a minimum, a local minimum instead of the global minimum. We can also diverge sometimes. We have problems with overfitting. And usually the data set, they don't represent the whole data distribution that will actually be in your final application. So there can be a shift between what you train your model on and what you test it on. And this is also a big field of research. And so, yeah, like I said, so now choosing the right building block is also very important. So if I use just my linear model right here that I presented before, y is equal to theta times x, I'm not going to be able to do very interesting stuff. And so those building blocks are actually very important. So I will leave the floor to Sylvia.
Right. And we're going to deep dive into deep learning. But maybe before we deep dive into deep learning, are there any questions in the rooms? Was it clear enough? Was it too technical? Happy to have any feedbacks? Any questions?
Super clear.
Super clear. Okay, amazing.
It's perfect.
Amazing.
And the class imbalance is going to be useful for us.
Yeah.
Right.
Yes. Yeah. Very good.
That happens quite often, right? The road example is a really good example, and we're going to have the same issue tomorrow, because tomorrow in the hands-on we're going to do semantic segmentation of wildfire, and usually the wildfires represent only a few pixels in a large image. So you will have the problem of class imbalance, and we're hopefully going to find a way to tackle that issue.
Transparent.
Great.
The division between the data sets of the test validation and training, sorry, is this random?
So usually we try to not make it random. So the idea is that it should be separate sets. So the training set should not overlap with the validation set and for the test set. That's one thing. Now, for instance, when we're working with video data from sports events, for instance, this is very clear. We have different games, and inside those games, we're going to extract images and annotate stuff on them, right? So we have one video that comes from maybe the final of the 2022 World Cup in Qatar, one game from the Champions League, and so on. The way we try to separate is not to have images that come from the same game to be in separate sets. And why is that? Because when you test it on new data, it's going to be something that has never been seen before. So if you have images in your test set that are from the same game than the ones from your training set, you also have some kind of overfitting between the two. Still, you need to have equal representation of the different data distribution that you have inside each of these sets. So this means that if I have, I don't know, only satellite images from Europe in the training set, only from Asia in the validation set, and only from Africa in the test set, I'm not representing also my inference properly, because I'm going to evaluate a model on a data distribution that is completely different from its training. So there are some rules to follow, which is basically try to not mix the same kind of event, let's say, so one flood, for instance, you're not going to separate it in one flood, yeah, let's say, in the region here, you're not going to separate the patches and then split them across the different sets. Simply because if another flood happens, you're not going to have part of that flood annotated in the training set. So yeah, there is some rules to follow here. So very good question.
Also on training, is there a way to also kind of iteratively train the models? So you train, you validate, or you validate, then you use perhaps the result, and then you train again the model. And when you decide to stop training your model?
That is an excellent question, and it falls within the. So I talked about here fully supervised learning. This falls within the same supervised learning framework that we're going to see in a few hours, and also the active learning framework, where you first start with a small set, then you do some prediction on the remaining set that you have not annotated. The model, you correct the prediction by hand, and then you retrain the model on the previous set, and you can do that iteratively. So this is this is doable, and we're actually going to dive into that part later. Yeah.
Maybe a last question about the overfitting that you are referring to. It's also something that you need to detect at a certain point that you are overfitting your algorithm. So do you have some indicator to detect that at the right time?
So actually the best indicator is this validation loss. This is the most commonly used. So when the validation loss decreases, it means that you're still learning interesting stuff. When it starts increasing, it means that you're overfitting. This is a very good indicator of overfitting.
Usually that's why we try to separate the training set and the validation set, because you want to train on the training set and you want still to work generalize well in your validations and in your tests. And the interesting thing is that those notions starts to be a bit more and more blurry over the last years for the simple reason that the data sets become so large these days that actually your training sets can be the whole world now. So the validations and the training actually kind of overlap, and it's a bit unclear nowadays if we talk about ChatGPT, for instance, or the model SAM, for instance, or all those foundation models that seems to work in all the cases, if you are actually able to generalize to anything, or if you have actually overfitted to all the data available in the world. It's like we have models that are so highly, a lot of parameters, I'm talking about billions of parameters now. We don't know if we're actually generalizing to the whole world, or if we actually are overfitting to the world. And the question becomes, is this becoming a problem actually or not? Because if we have a model that is generalized enough, maybe actually I'm actually fine with overfitting. So this, those definitions in the realm of supervised learning, we try to avoid overfitting. But in some cases, if your training set and your validation represent all the cases you have in the world, maybe overfitting is a good thing. So because this is like I would say a new trend that appears over a year and two, and it's a really good question to actually answer. If we overfit to the world, is that a problem? Because it will work in all my cases. It won't work.
The overfitting in this case will find classification better than we humans can classify.
It could.
It's a question outside overfitting, actually. So
Right.
there are models that are not overfitting the data that are better than human in some cases. That's for sure. Yeah.
But yeah, so it's a blurry thing. This overfitting thing, those days, it's a bit blurry. Do we want overfitting? Do we not want overfitting? If you overfit to the world, is that a problem? Of course, you want to apply your satellite imagery, for instance, on Mars, for instance, if you generalize, but is that a problem actually? If you actually can overfit to all the data you would ever possibly acquire in Europe, for instance, do you mind overfitting in Europe if your use case is actually only Europe? So sometimes overfitting to specific regions is something that perform very, very well in that region, but we know that it won't work well in Asia or in Africa or in the US, for instance. So it's a choice eventually. It's a choice eventually. There is different type of overfitting. There is overfitting from that. I think the rules of the validation lost over overfitting, and if the validation and the training are in the same distribution, if they are in the same distributions, you do not want to overfit. That's for sure. But if they are from different regions, maybe overfitting sometimes is not a big issue. So it's a philosophical question. I would say. Any other questions?
No, online, I don't have any questions.
All right, that's great. Okay, so now I'm going to actually deep dive, and I think after everything, I still maybe need like a half an hour, and then maybe 20 minutes on that part. We're going to have like a small break. It's good for us to also have a small break, and we can take like Q&A and have some coffee, I think, back. But I would just like ask a bit of your time. So basically, now what is deep learning? And originally we defined deep learning as, so we have understood what it means to learn a model. So optimizing the parameters is actually the process of learning, of training an algorithms. And in deep learning, we actually want to learn the features and the mapping from those features to the outputs. So you want to learn the classifiers and the inputs that you're actually interested into using for that classification. And deep learning is nothing else than the fact of using deep neural network that I'm going to define. So a network of neurons with a large number of layers and a large number of neurons. Deep learning is nothing else than machine learning with a lot of parameters. So instead of having only one parameter in the example of Anthony was saying, we might have millions or billions of parameters. So what is a neural network? First of all, like from a biological definitions, neuroscientists believe that the human brain has a hierarchy, a network of neurons that is responsible for visual recognition. You have people working into how does these neurons are actually connected to each other. And basically our brain, for instance, again, taking again the example of the numbers on the left that we can see, our brain somehow has learned that this combination of pixels means that is the number 8. And this is something that we just have learned from our school, like from years and years of training in our daily life. But what is a neural network exactly? Neural means it's based on the model of the neurons, in particular the perceptron that I'm going to present. That is a paper from 1956, as far as I remember. So it's something that is extremely old. And it's nothing else than a linear combination of some input with an activation that breaks the linearity. I'll explain that. And then what is a network? The network basically tries to answer how are those neurons connected to each other's. And they are defined by specific width of the layers and a specific depth, which is the number of layers that will provide you with the desired output. The neural network is a model. It's a model that is able to learn some content that maps an input into an output. So a neural network is a tool that model the algorithms for computer vision or any deep learning approach that can be optimized in the way that Anthony has explained that. So let's go into the model of a neuron. The architecture of a neuron is defined by the perceptron, I said like 1956, where X is the input or the intermediate representations that is fed to the network, to the neuron. So capital X will represent here a vector of informations that can be spread into X1, X2, up to Xn. Then we have a linear combination of X. The neuron actually takes all the input X1, X2, X3 until Xn and build a linear combinations of that vectors into Z. Z is a linear combination of X. And then A, which is a sigma function of Z, is the activation of Z. It's called the activations, and it's what breaks the linearity of that linear combinations, which is extremely important to learn nonlinear functions. I'm going to show you how it works. So, what's an input features? In images, like the simplest way of defining an input features, as I told you, the image of the 8 on the left is nothing else than a list of numbers ranging from 0 to 255. One of the most stupid way, actually, to represent that image is basically to flatten all the pixels. So I think this is from MNIST, so it's 28 on 28 number of pixels. That's 750 something pixels. That basically has an intensity ranging from 0 to 256. So you can flatten the pixel intensity of the image and use that as an input. So X1, X2, X3 until X750 and something would be the input of that neuron. The second way of also representing the input could be, instead of the flattening of the pixel intensity of an image, could be like some quantifiable intermediate features. Remember, in the machine learning realm, we actually told that actually the features that are fed to the classifiers could be something handwritten. And you can actually learn some concepts in a fully natural way through the neural network. Some concepts such as the curvature or the dimension of subpart of the shapes, doing some shape analysis. For instance, the number 9 is nothing else than a circle with a bar. The number 8 is actually 2 circles. So if I have a way to define some quantifiable intermediate features, I could also consider them as an input to my neurons. And I might actually learn those representations with other neurons that are fed to the new neurons to basically interpret what is a 9, what is an 8, what is a 7, and so on and so forth. As I was mentioning, the linear combinations is basically taking all those input from x1 to xn and learn basically just a linear combinations. So all W1, W2, and until Wn, and the bias, which is the offset of these linear combinations that we were talking before with a very simple case of Anthony, where we only have one parameter is W1 and not even a bias to define the offset of that linear regression. We can actually learn that from multiple inputs, from x1 to xn. So the parameters that are the dark green square are basically parameters that are learnable from my neuron. So in that specific case, if my neurons can accept n different inputs, I would have n+1 parameters that I can play with my neurons, and then I can train my neuron with in order to create a linear combinations of my input. Then we have an activation. Basically, the activation is extremely important because it breaks the linearity of the linear combinations. And we'll see later that if we stack multiple neurons, if I don't break the linearity, a linear combination of a linear combinations is nothing else than against a linear combinations. So you actually can stack as many layers or as many neurons as you'd like to. If you do a linear combination of linear combinations, it's a linear combination. But if you break that linearity with different functions, this function sigma, we can actually, the linear combination that is activated and then a linear combination, it breaks that linearity and can learn non-linear functions. So that specific function is extremely important. What does exist in the literature to break the linearity? The most famous one is the ReLU, the rectified linear unit, which is mostly used, which is defined as the maximum between 0 and my input. In that particular, x here does not represent that, x actually represents the z here. So I basically take whatever I have in my input here. If it's negative, I put the value of 0. If it's positive, I basically put the value itself. There exist other activations, in particular the hyperbolic tangent, sigmoid, for instance, the softmax also is used for the classifiers, or the leaky ReLU. There is a lot of literature in trying to finding what's the best way to break the linearity of that linear combinations to create the value A out of the input X. So then how neurons are connected to each other. So that was the model of the neurons. I'm not inventing that. It was defined already in the 1956 by, I forgot whom exactly, to be honest. But then neurons are stacked together, and they are stacked together in layers. Layers would be multiple neurons that take the same input from x1 to xn and creates multiple outputs. So I basically put them into a layer. I take the same input x, and I use all those x in the different linear combinations, maybe the different activation of the same activations, and I create a new output out of that. That is basically the role of one layer defined here, where I would have different value of x here that represent, like, this is one neuron that will define a new value activated, a new value activated here, a new value activated here, and so on and so forth. That is a way to basically learn a lot of parameters. Every single arrow here could represent like one parameters to fine tune, to learn. That would basically go from one input to one output. These layers can either be intermediate representations, so I can take all the input of my pixels and extract a hidden representation, intermediate representation, what we call from a hidden layers. That is not something that I actually have any control of, but I would know that this input, this output will be the input of another neurons that could be useful for me to classify whether it's a 1 or 2 or 3 or 4, so on and so forth. In the last layers, we also have a specific type of layers that is used as a classifier. The classifiers are typically a specific type of activations, which is called the softmax. It's actually illustrated here. If I have just one layer here and I want to classify my 784 pixels, whether it's the number 0, 1, 2 until 9, I would like to have like some probability functions that told me from a range to 0 to 100% how confident it is to be a number 0, number 1, number 2, number 3. And one way of doing so is by using a function called the softmax. I'm not sure if I have the equation here, but it's basically the exponential of the value of one of these outputs divided by the sum of the exponential of all of them. Why is that interesting? Because the sum of all the predictions for every single output will be equal to 1, and I would actually have a confidence score for every single output from 0 to 9 of how confident my neuron, my neural network or my classifier would be to classify that entry as a specific number. And that is very useful to define the loss. You can actually define the loss of the mean square error, for instance, that defines that I'm expecting the output of 0 here to be 0. Here I'm expecting that to be 0, so I expect that to be 0. At the number 8, I'm expecting that to be 1, and at the number 9, I'm expecting that to be 0. And how far I am is basically how close my confidence are to the output I'm actually expected, which can be modeled as the MSE loss, mean square error loss that Anthony presented before. Okay? So neurons are stacked into a layer. So one layer of neurons maps one input into an output that can go from any dimensions, 784 pixels, for instance, to a mapping of 10, for instance, neurons that represent the outcome from 0 to 9. Then the layers are eventually stacked to create a network. And when we talk about deep neural networks, we are actually talking about a network that has a lot of hidden layers that have intermediate representations that I somehow don't care much about what those hidden representations are. I will let the neural network or the training process finding the best hidden representation, intermediate representations, such that my output at the end would correspond to what I'm expected. So those are all the parameters. Every single arrow you can see here are basically one parameter that you actually have to learn, basically. So that's the problem of like high dimensionality. Before we're optimizing one parameters, which was the theta, then we try with two parameters, it looks like a bit, but here we are talking about maybe hundreds of thousands of parameters in that very, very shallow and small network. So basically the layers are stacked to create a network that defines the depth of the network. The more layers there are, the deeper the network is considered. It represents hidden representations in the between, and it's basically a compositions of linear combinations that are activated. And again, if there's no activations, stacking multiple layers, basically a linear combinations of a linear combination is still a linear combination. So the activation is extremely important to break the linearity from one layer to another. And usually the deeper you go, the more abstract and the more non-linear you can actually go to, and you can actually learn some really interesting functions that goes beyond just the linear regressions that Anthony showed. And when I talk about linear and non-linear problems, this is basically a classifier where I want to classify the dot in some space where I have two value x and y here, the two axes that represent maybe like two intensities of a pixels, or two values of, I don't know, I have a temperature and I have the vegetation index, and I would like to classify whether it's a crop or it's a building, for instance. I would actually try to figure out which green dots actually belongs to the green dots and which blue dots belong to the dots. So I would like to find that line that separates the green to the blue. And this is a linear problem. I can just draw a line that split that. But in most of the cases, you actually have non-linear problems where a simple line cannot distinguish between class A and class B. So having non-linearity in our neural network is extremely useful in those specific use cases. And before having a small break, this is my last slide before the break, I would like to introduce you to a really cool tool to actually have this insight on how to classify blue dots and orange dots. It's made in TensorFlow. TensorFlow is the library from Google that provides you some tools to train neural networks and in Python and in C++ and different languages. And in that specific tool, basically you have different problem classification here, for instance, where I have different dots here. I have different representation of my feature space, and I would like to classify the blue and the orange. Let's take that example, which is a very linear case, and I can define my number of hidden layers, my number of neurons I'd like to do, and I would know what I would actually do. No hidden layers, directly take my x and my value. So this is like two ways. So the value x and the value x2 are basically the two dimensions that basically relates to here. And here I can actually, even having an activation which is linear, which means like no activation at all, here I can train a neural network that will basically split the blue and split the oranges in two different parts. And we actually are training at this number of epochs, how much is actually used to train. I think there is a way to show which one are the test data, which one are the training data. So the dots you see here are actually the training data, and here I can show the test data. And the loss of that training is actually equal to 0. So I found an exact solution, fully linear, to basically split those two sets of points as just a linear combinations of x and y. It's not wrong, it's just a line. But this is not representative of most of the cases. So if I look at a different problem, like this one, for instance, if I still take the same neural network here and I actually just play, it will be extremely difficult for me to split that work, that space into two areas where I have the blue dots in one region and the orange dots in the other one. In fact, I can train as much as I'd like to. My loss is basically stuck to some value that is not equal to 0. In order to actually have such a thing, you actually need to add some hidden layers, eventually add a few bunch of neurons, add an activations. Let's do like a ReLU. And if I just do play, there would be a list of linear combinations of activated with the linear combinations that would actually be able to split that into specific regions. And I'm just taking like the X and the X2 here, the values. If I had more neurons, I can have some shape that is a bit more circular and a bit more non-linears. And the more neurons, the more non-linearity I can actually introduce in that field. In some other cases, for instance, here, which it's extremely difficult to actually split the orange dots with the blue dots. If I train that model, it would be extremely difficult to split that space into understanding which part of the space belongs to the blue dot or to the orange dot. So adding more layers in that case and a lot of neurons per layers is one trick that basically helps you learning some functions. Is it working? Hopefully it's going to convert at some point into something. You can see like the loss is actually decreasing. Both the training loss and the test loss is actually decreasing, into finding some region in blue that kind of like learn the spiral. It's not that bad, to be honest. Mm-hmm. And here the training loss is done. And here we have actually learned like a blue region that can define all the blue dots and the orange dots and separate them. And I think the loss is actually not that bad. So adding more layers can actually represent some better way of classification. That's just a toy example. I invite you to play it around with those tools. It's a very nice way to understand like how deep learning works and how a neural network made with multiple hidden layers, multiple neurons per layers can actually classify the world in multiple places. That's
super. I have a quick question.
Yeah.
Is there a way, and is it interesting to understand what happens in the intermediate layers, in the hidden layers, to understand what is he doing?
Right, absolutely. Actually, in fact, I think I'm going to look at one image that I don't have in that slides, but intermediate layer representation in computer vision. There is like some paper that try to analyze what is inside those intermediate layers. And there is one paper.
You're not sharing.
Yeah, sorry. Sorry, I need to share my screen again. For some reason it was disconnected. Here I am. This is someone that after training I'm sorry, the image is actually terrible. Oops. It's on ResearchGate. So that's a visualization of what it actually learns. That's not the best example I had in mind, but when you have like multiple layers in computer visions and using convolution neural network, by looking at the intermediate representation of the filter of the convolution neural network, I have not introduced that yet, but basically you have some abstraction of the object itself. For instance, you can imagine that if you want to classify a car and a plane, for instance, the intermediate representations might activate very well at the place where the wheels are. So in that intermediate representation, you can understand that as a way to, in a fully unsupervised fashion, learn some features that are highly representative of my objects, that would compose my objects. So for instance, like if you go to the last layers that's able to classify a plane with a car, for instance, if you go one layer back, there's high chances that one of these neurons are actually able to identify where or activate whenever you have a wheel, for instance. And if you actually have that, and if you have like somehow information that there is two wheels that is visible, plus maybe a windshield, plus maybe a blinker, maybe some lights, or maybe some roads, you can actually classify the whole image towards this is a road, this is a car. If you go maybe, if you have like a plane and you identify that there is a big engine and some wings, for instance, some area of the image that has that, you would actually have in intermediate representations that will tell you, hey, I saw a wing here, I saw an engine here. Maybe there is high chances that in the last layers that take this intermediate representation and tells you it's a plane. So this is basically the insight of the intermediate representation.
So it's basically also understanding the parameters that it is taking into consideration to do the classification.
Right.
It can help us to define
some explainability as well.
It can help with explainability. In fact, explainability is a big topic in artificial intelligence. It goes way beyond satellite imagery. And for instance, in autonomous navigation, when you have self-driving cars, you have deep neural networks that, given what you see, will just regress if I need to accelerate, brake, or turn right or turn left. That's great. Maybe like your cars can actually learn that very well, where to go next based on what it sees where the road is. But if it doesn't go to the proper directions, the question becomes why it hasn't done that, and there is no answer for that. So there have been some research that I've been participated like 5 or 6 years ago, for instance, that tried to break that and introducing actually interpretability to neural network by creating modules. If I want my car to go to a specific, I want to drive itself, I want to have a module that will just look at where the road is. Then when I know where the road is, I will also have a model that will look at, is there any cars in the road as well? Then I would take this information, so I would have a specific model that will be just trained on that scope. Where is the car next to me? Where is the road? And then I would take this information and say, okay, now that I have this information, where should I go next? So it will actually look at the picture where the car should be next. And this will be another models that will be trained just to go from those points to, okay, I'm here to that point. What is the type of acceleration that I need to do? Is it going to turn my wheels on the right or on the left? By creating this modularity, you actually introduce interpretability, and you can explain what's happening in the model by explicitly telling it, look, I'm actually if I did something wrong at the end, I can trace back what has been done and try to identify, oh, I actually did a mistake here because I have not detected that there is a car. So I would know that the issue comes from the fact that there is no car. So people are trying to do that these days.
Yeah, and we also have some work that we've done together where we are actually linking this hidden feature representation to a large language model and learning actually if I have a specific like activation of those neurons, what does it mean in terms of why the network took that decision? So we trained neural networks to recognize different type of classes, but also to have a language model that we can query and ask, why did you take that decision? And it will look at the activations right there and produce some text to say, oh, I took that decision because of this, and that actually represents somehow what is hidden in those layers. So we also did some work.
The explainability bit domain.
Exactly. Exactly.
That's great. Yeah, to hear that. There were questions also?
Yes. So, two questions. One from Quentin. He says that we usually hear about overfitting, but very rarely about underfitting. Right. Have you ever had issues with underfitting? And it's not much a problem in terms of remote sensing, especially with self-supervised learning, contrastive learning, etc. But he's curious as how you would proceed with underfitting, apart from collecting more data or augmenting the data in the most time.
Yeah, actually, underfitting just means that you have possibilities to improve the performance of your model. This is what it means, right? So if you continue training, it means that you have not yet reached this part where the validation loss, for instance, is low enough. So yeah, that's actually a very good question. First is identify. Knowing that you are underfitting may be difficult sometimes, because here I'm showing a very simple example. So the red line is a bit complex, right? But in practice, this is not the case. What's going to happen is that you're going to have your validation loss that is a bit erratic as well. So the training loss and the validation loss might be erratic. And so you might see, I think we've seen it if you were paying attention on the top right part when Silvio was playing around with the TensorFlow program, but actually at some point the validation loss was increasing before decreasing again very rapidly. Right there, you can see it. Yeah, exactly, and around that part. So there, clearly, if we stopped training before, we would be underfitting. And yeah, this is a very broad, very broad topic. It's more like everyone has its own cooking recipe, knowing how to avoid that. So one way is to play on the learning rate. So I think this is one of the most important parts of training neural networks, is to actually find a good way to tune that learning rate. And so here we explored one example where the learning rate is stable throughout training. Actually, when you train big models, this is not a good strategy. What you will do first is start with some initial learning rate, increase it with a warm-up period that will point towards that different areas of the search space of your features, of your parameter space, and then reduce it in some kind of sinusoid or cosine way to increase and decrease and increase and decrease, and this helps to converge towards local minima and maybe jump towards another local minima and so on that is better than the previous one. And so clearly this is to avoid underfitting. But this is more like cooking recipes.
And I think the second part of that question was in regards to self-supervised learning and contrastive learning. Exactly, yeah. So basically, as Anthony said, like this optimal training at validation, whatever is after the epochs is basically overfitting. You have just overfit on the training data. Underfitting basically at the left side. You could actually train more epochs and actually. In self-supervised learning, the task of self-supervised learning is a bit tricky. So self-supervised learning is usually meant for feature representations. Before we actually talked about fully supervised training, where basically your end task is just to reduce that training loss, and then you have a model in the fine. But as mentioned by Anthony, you usually don't start from scratch. You actually can take some pre-trained algorithms, pre-trained weights for your networks that you will just like fine-tune for your own scope. So typically, when we talk about GeoSAM versus SAM, GeoSAM is fine-tuned on geographic data is the fine-tuning of an algorithm that was pre-trained on generic data. There is some really interesting research that basically says that it's unclear. So it's unclear if self-supervised trainings is basically just training for that representation. I don't use a single label, but I will learn some meaningful representation that will identify what a wheel is, what a windshield is, what a wing is, without giving a single labels. Then I don't care exactly what is the final task of that, because I will just use the representation, the encoder, the first maybe layers, to actually use that as a pre-training to fine-tune the whole network for my downstream task. And in that specific case of self-supervised pre-training, it's unclear if we need to go up to the optimal validation loss, because if you are in underfitting, you are still in the space of your parameters where you're not in your global minima. Because the problem if you're in your global minima, it might be hard to jump over or to go up the mountains against to find what the global minima is for your downstream task. So being in underfitting, so basically in that regions here, for instance, might be better for the downstream task that is in hands. So it's a bit more complicated than that. I don't know if I have not lost like people, but
we're going to talk about self-supervised anyway in the next part.
Yeah, that's true. But really good questions, very important.
And another question from Lucas, is there a way to handle errors in the input data? Say telling a model 5% of the data are not labeled correctly.
Right.
Exactly. And this is actually a very good number, because it's actually what we believe as a good data set is a data set that contains below 5% of errors. So if it contains around or below 5%, we say it's a curated data set and that it's good. So most data sets like ImageNet, MNIST and so on, they contain errors, manual errors from humans, or sometimes ambiguities that are difficult to say that this is a cat, this is a dog, for instance. And what was the second part of the question, sorry?
So
how to cope with that?
Yes.
Yeah, so that's also a very good question. So here in the stochastic gradient descent that you have here, what is going to happen is that actually your loss surface is going to change at every iteration of this mini batch gradient descent, which will also avoid being stuck in some minima that contains error. And now,
and here, the fact of using batch, it can say is like basically I'm going towards the directions that maybe 10 or 20 images agree on. Mm-hmm. So if I am actually taking, I don't know, like 20, 30 or 40 images to go to a specific direction, I'm actually taking the average directions that all the images tell me to go. So if I have 40 images in my batch, they might all tell me to optimize in the specific directions. Some images of the cat tell me, oh, go to that direction because I will overfit on the cat. The dogs will tell me like, oh, go to that direction because we'll overfit on the dog. If there is one direction for one sample that goes to the bad directions, the consensus somehow, the other element of that batch will tell me to go towards the proper direction.
Yeah.
So that's what I want.
And also there is a whole field actually of techniques that are trying to learn from noisy data. This is also a whole field, and we had some work that I did in 2018, where basically, for instance, we had I don't know if you can get back to the MNIST example with the eight digits. So like you were, Silvio was mentioning that the objective was to have 0 everywhere at the output of a neuron, maybe with the output. Yeah, with the output is that you wanted to have just a prediction of 1 for the 8 and 0 for everything else. Sorry, there's a lot of slides. But actually what you can do as well is to introduce some kind of, here it is, right here, that introduce some loss function that allow doubt of the neural network. So one way we introduced that in 2018, for instance, was imagine that this 8 was labeled as a 2, is that I would take among the 2 highest prediction of my neural network. So here it would be high for a 2, let's say, for an 8, sorry, but maybe for the label is at 2, and I'm going to say, all right, it is a 2, but the network seems to really believe that it is an 8. So I'm going to actually let him decide between 2 and 8, whatever it can do, and I'm not going to penalize it for saying this is an 8, even though it was labeled as a 2. So you can actually introduce some doubting mechanism inside the neural network through the loss function. So I'm not going to go into the technical details of how we do it, but this is available online. But basically here, the idea is, you can introduce some doubt through the loss.
And then Lucas asked a following questions. Maybe going back to the training data set, is there a rule of thumb for how big the training data set should be for supervised learning?
Excellent question.
It's very difficult to answer that. It usually is depending on the complexity of the task in hand. If you just want to classify cats and dogs, you might need, I don't know, 20 images. But if you want to classify 20 different breeds of dogs, you might need way more examples. It depends on how different are those data. Second part is also, it depends how diverse are your data. I often take the example of the cat and the dogs. If the cat is white and the dog is black, having more black dogs and white cats doesn't help you much. But having more diversity in that sense would help. Having like a yellow cat or a brown dog would actually help you understanding what's a dog and what's a cat. And there exist some mechanisms that we're going to also dig later on called active learning. So if you're in a realm where you have access to a lot of satellite images, let's say, you have annotated, I don't know, everything in Luxembourg, let's say, and you want to test something in Belgium, you can actually identify region in Belgium that is very different from what you have in Luxembourg, where the network is actually confused, and he knows he's confused, to include in your data set. So here is actually a way to find in your data set which data to annotate next in order to minimize the amount of annotation you need to do, and still retaining as many diverse information.
And there is actually a good way. So let's imagine you have one data set and you want to know, if I collect twice the amount of data, am I going to improve the performance or not? This is a question that you could have, right? What you can do is take this data set and reduce it. So you remove images from it step by step, and you train a model on different subsets of this data set. So maybe one with 1%, 5%, 10%, 20%, 50%, 75% of the data that you have. And you take a look at, on the same test set that is still separate, the performance that you have. If you have something that is growing in performance with the number of data, it probably means that adding more data will improve your model. If you have something that is doing a curve a bit like this, so stabilizing at the end, probably means that including more data will not improve the model. Now, of course, this is model dependent, because if you change the model, you take a bigger model, maybe it can learn more stuff, and so yeah, it's really model dependent, this analysis, but it's still a good way, and we do it in our research. It's an engineering way to know if more data might be better or not, and if you should invest in annotating more data or not.
Perfect. Okay, no further question. I think we can break for a coffee now. We are a little bit late, but I propose that we come back at 10 to 4, so we have 15 minutes of break. So the people on the audience, we will come back at 3:50, so 10 to 4 for the second part of the training. Thanks.
Thank you.